as the recording starts and we're ready for what will become Chapter 17b, the special senses, with an emphasis on hearing and balance. Now, our ears are pretty obvious in their location on the sides of our head. They are there to collect a different kind of wave from the eye. The eye is electromagnetic radiation that can cross vacuums. The ear takes a wave type of energy that's being transmitted by actual physical pushing of the molecules. And these are called sound waves. To have sound waves, you have to have some material. So sound can move through solid, liquid, and gas, but it can't move through a vacuum. The inner ear also is the location that we use to sense the direction of gravity on a constant basis. So no matter how we're using our body, no matter how we're twisting or turning or bending or rolling, we're constantly being fed information on which way is up. That's the single piece of information that we need in order to achieve a righting of our balance or the maintenance of our posture and movement. So everything we call athletic movement or performance, balance, and posture on an everyday basis depends on the workings of the inner ear. So let's take a look. Here is the entire structure, starting with the spongy bone here in the temporal lobe. This is the auditory meatus, external and internal, that we studied when we talked about the skeletal system. And surrounding this are the soft tissues, the fat and the elastic cartilages that form the shape of the inner ear, leading to this ear canal. So we divide this into three parts. The external ear is shown here from the outside opening all the way into the tympanic membrane. This is a very fine membrane stretched across this ear canal. Now, sound waves are going to travel down here, and when they hit the tympanic membrane, it vibrates back and forth. The middle ear starts with the tympanic membrane, and it ends here with the oval window. Now, connecting those, the three auditory ossicles or hearing bones, the malleus, the incus, and the stapes, are suspended here in the middle ear by ligaments and a few muscles that can control their movement. And the job of the auditory ossicles is to take the vibration of the tympanic membrane and to vibrate back and forth, transferring that vibration here to the oval window. So if the tympanic membrane is going like this, we see a movement like this, and a movement like this, and a movement like this, transferring that vibration to the oval window, the job of the middle ear. Also, there is an opening, the auditory tube, that connects to the nasopharynx to allow the pressure to equalize on the outside and inside of the tympanic membrane. The internal ear, embedded here in the bony labyrinth of the internal ear, we find two distinct sections of a small bony organ. Now, this part that looks like a snail is the spiral organ of the cochlea. And this is where sound waves are interpreted and detected. The upper region here, this opening, is called the vestibule. And here we see three tubes that are basically formed into loops, returning to a central joining point, and they are organized sort of like the axis on a 3D graph. This is called the vestibule, this opening, and these structures up here, the semicircular canal. This is also the petrous part of the temporal bone. Sometimes they just shorten that to the petrous bone. The reason it's important is that it's generally the part of a skeleton that they use for isotope examination and radiocarbon dating. The middle ear is shown here. You can see the tympanic membrane, the inner surface, and the connection to the basic auditory ossicles. Now you can see they have to be held in a particular place for this vibration to be transmitted through this almost Z-shaped configuration. And you can see in the drawing, they've drawn in only the parts they want to emphasize. These are stabilizing ligaments that hold them in place but allow them to vibrate. So the vibration of this membrane pushes this back and forth, and the oval of the stapes back and forth to translate that vibration to the oval window on the side of the cochlea. This tensor tympani muscle is a muscle that can relax completely when sound volume is low. So this is just barely vibrating, and you want these to move freely. This muscle is relaxed and moves as freely as it can. But if you all of a sudden step around the corner and there's a jackhammer running, that loud sound will cause this membrane to vibrate quite a bit. And that's where the tensor tympani comes in. It tightens a little bit. It sort of restricts the motion so that you can tolerate a higher sound. And it does not tear this, this delicate apparatus of the middle ear into pieces. Now the oval window, I just want to point out, this is the opening to the auditory tube. Excuse me, let me get my mouse in the right position. Auditory tube, that's the air pressure vent from the nasopharynx. And below it, another depression called the round window. Now the round window is going to allow vibrations inside the cochlea to vibrate the round window so that they don't go bouncing around inside the cochlea. Now these are just like waves. In the bathtub, you know, you push the water, and you watch the wave go to the other side and bounce off, and back to this side and bounce off. Basically like some of the video games that we see where things bounce off of edges like pool table balls. The structure of the internal ear is the external and internal auditory meatus in the vestibule, and inside it you find the bony and the membranous labyrinths. These are the places where the sensory receptors are shown, in this case in purple. Dividing these spaces, like you see the spiral organ, is shown as consisting of a continuous blue side which spirals up all the way to the apex, and then a purple side that spirals back down on the other side. Now, the junction between that is a membrane that will be vibrated by sound waves. I'll explain this a little more completely, but just quickly. The volume of the sound is going to affect the amplitude, how much movement back and forth there is. The louder the sound, the more movement. The frequency, the wavelength, is going to determine how the waves are set up and what part of that membrane they stimulate. I'm going to translate that later into the frequency of the sound or the pitch. Now here in the membranous labyrinth, we see these semicircular canals oriented like the X, Y, and Z axis on a graph. Within that, we are going to see a continuous liquid medium leading to these cristae, these particular sacs of sensitive cells. As we hold our head in a certain position, that produces pressures on these 5 detectors. As we change the position of our head, like nodding our head, dropping our chin to our chest, that changes the pressure in these 5 sensitive areas, which our brain interprets and reports the change in the position of gravity. The first part of this organ, hearing, takes place in the cochlea. And you can see that it is very much a spiral moving around and ascending toward the center. But up here at the top, do you notice how that blue arrow points into the chamber for the red, and it basically goes back down the other side of the membrane? Now we're going to translate that structure into hearing in just a moment. So coming down through the organ in the way shown by this blade or plane, you can see 2 complementary channels that are running from here to here to here to here, and then reaching the top, where at the top the fluid of one channel runs continuously into the fluid of another. So what you're seeing is kind of a way up and a way down if you travel the whole channel. Here at these critical junctions between the 2 channels, you see the detector organs here, 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 at each location, lining this spiral organ all the way up. At the base of it, you see the cochlear branch of the vestibulocochlear nerve coming up the center of this bony organ and branching to provide nerve connections to these sensitive membranes. The tectorial membranes and the vestibular membranes are shown in this drawing. Let's make it a little simpler. If we take a cross section showing the different tubes right here in the cochlear duct, the tectorial membrane is where we're going to mount our sensitive cells, right between those 2 adjacent tubes. If we take this structure where the pointer is and blow it up, we see a basal membrane and a series of cuboidal and columnar cells mounting these hair cells so that they stick up into this space. You see the delicate hairs covered by a tectorial membrane because the vibrations of the sound waves would actually damage them. So they're somewhat protected. You can notice the connections at the base of the hair cell going back and collecting and eventually becoming the nerve fibers that are running to the cochlear branch and carrying auditory information back to the auditory cortex on the temporal lobe. Now let's look at the sound waves themselves. Actually, what's happening, that sound we hear comes from the vibration of this tuning fork basically piling up a line of molecules in the air and then launching it off as it retracts back in the other direction. As it retracts back, it produces this kind of blank area, and then it pushes forward again. So these are called bands of compression, where you've pushed the molecules together, and these are called bands of rarefaction. And they will move with a certain force through the air and into the ear canal. When we talk about a wave function, we talk about the amplitude. That's basically the height, as you can imagine. If the amplitude is very great, it's going to push a lot of those air molecules and the energy is going to increase. That's a loud sound. If you push only a few, then that's a very short peak, and that's a soft sound. The distance between the peaks is one wavelength. Put the peaks closer together, and that is a sound of high pitch. Spread them out, and that longer wavelength reflects a sound of lower pitch. Now, this simplified drawing is going to show you the hearing process and try to combine many of these elements. It's a very, very simplified drawing. The actual cellular and bony structure is really quite a bit more complex. But I'm going to try to illustrate how a particular sound, this sound shown here, with this amplitude and this wavelength, is going to affect the hearing system. The amplitude is going to cause a specific amount of vibration back and forth by the tympanic membrane. And so the actual travel back and forth is due to the volume of the sound. The speed of that vibration back and forth is going to be determined by the wavelength or the pitch. So we're setting up a vibration that is transmitted through the malleus, incus, and stapes connection and produces a series of vibrations in the oval window that are transmitted on the one side of the cochlea. Now you'll see up here, they've simplified the spiral organ into kind of one curl up and one curl back. But all along here where we have the cochlear duct with the endolymph and the vestibular membrane, we have these detection sensor cells, the hair cells. Now, waves have a kind of an interesting property. If two peaks run together, then the wave gets taller. If a peak hits a valley, they cancel each other out, and the wave disappears. So as we're transmitting this wave, it's basically moving around this spiral organ, and its amplitude and frequency, that means the particular quality of the sound that is entering the oval window, will cause it to converge on one place in this membrane. It's shown here as position 5. Now, it's the character of the sound that causes this to be the location that is stimulated right now. So this vibrates up and down, transmitting that vibration across to the other side for a return back to the round window. This is where the wave energy is going to vibrate this round window and basically be stopped. Now, this distortion of the basilar membrane is then only going to stimulate hair cells in this region of the cochlea. And those hair cells are connected to specific nerve endings in this cochlear branch. Do you notice how the cochlear branch fans out? These fibers connect here. There are fibers then that connect all the way around to a specific place in the spiral organ. And those that connect here then will be activated with action potentials and transmitting nerve impulses through the cell body and axons of those back toward the central nervous system. Now, this is important that the spatial organization of the cochlea responds to the wavelength and amplitude of the sound and sends specific signals through specific nerve endings, not all of them. Now we just have to trace those nerves that are carrying the sound. Another way of looking at this is that the high frequency 1600 hertz would vibrate here close to the oval window, so that loop of sound would be right like this, whereas 1000 hertz lower frequencies are going to be way up toward the top of the cochlea, vibrating the hair cells in these locations and bringing that energy back on the other side of the basal membrane to the round window. If it's 6000 hertz, it's going to start distorting the basilar membrane up and down like this. The the membrane does flux back and forth as the sound waves continue to kind of scrub on it. And the connections that you can see here are sort of color-coded. You notice how the different positions in the cochlea are labeled with colors: yellow, orange, red, to purple, all the way to the darkest purple at the top. Now, if you follow the fanned out nerve endings that are basically in the basilar membrane all along this spiral, you follow them back here, they're delivered here to the, if you recall, the midbrain, the medulla oblongata, where there's an auditory center. Let me reverse that back. This is ascends from each cochlear nucleus in the inferior colliculi of the midbrain up into these various nuclei, the reticular formation and the motor nuclei of the cranial nerve, and eventually up here to the thalamus and the geniculate nucleus, which is receiving this auditory information. Notice that the right side stimulation has crossed over to the left side and is approaching this auditory cortex that is right on this lower surface on the temporal lobe. This is the insula, that deep infolding that separates the temporal below, the temporal below from the parietal above. And the color codes show you that there is a spatial organization for the connection of those nerves from the cochlear branch. So if you start down here with high frequency sounds in the yellow region, those will be reported through nerves up to this region, the deepest region inside the insula, and will progress through the orange and red to the purple region. So that is how we discover the pitch of the sound, which is the location that it is delivered to, and the amplitude is directing our perception of the volume of the sound. Now, hearing and hearing damage responds to a kind of a natural range of sounds in our environment. Decibels, the lowest audible sound starts right above 0 decibels. A library or a soft whisper is 30. A quiet office, living room, or a bedroom that, importantly, is away from traffic, would be around 40 decibels. So going up through these lower decades, an air conditioner running at 20 feet, a sewing machine, 60 decibels, all of that is easily tolerable. But if you get to a place where the traffic is constant and it's busy, or you're approaching the traffic, walking on a busy street or in a noisy restaurant, if this is continuous and prolonged, it can begin to damage your hearing. The standard things of our environment that we built without considering very, very closely the effect on our hearing. Something like a subway, if you live in New York City or Washington, D.C., the older subways in New York City are very loud. The newer subway in Washington, they made attention to bigger spaces, and the operation of the trains is much quieter. Moving up through here, we encounter several things that are important to me, like 90 decibels, less than 8 hours of exposure is needed with a gas lawnmower. Think about those folks who go out and cut lawns all day. A chainsaw, I do a lot of cutting of wood for heat and run a chainsaw all day, but this reports that 2 hours without hearing protection is dangerous to my hearing. Rock concert sandblasting, or being near a thunderclap. Basically, those are very, very loud sounds. Gunshots. I grew up in a shooting family, so we took out rifles and shot them by the hour. And they are reporting here that immediate and intense report provides immediate danger to your hearing, and they recommend hearing protection. A very common experience is seeing a rocket launch. Now that we're talking about Mars, in addition to a base on the moon, rocket launches have become very pervasive on television. And here we say, if you're standing close to that without hearing protection, hearing loss of some level is inevitable. It's because the machinery is very delicate. The sound waves that move through the air are really very, very small forces. That's why the apparatus is reduced. But it evolved under natural conditions. You'll notice that as we go up here, the representative sounds become more and more products of our social and cultural development, the kinds of things that we commonly encounter. Within the inner ear, we have a sense of the direction of gravity and of motion. And this is something that can be confused easily. If you confuse your balance and motion sensors in the semicircular canal, you might suffer from a nausea and a disorientation called motion sickness. And the basic idea with motion sickness is to tell you, stop this right now. When we look here in the semicircular canals, we're not talking about vibration. We are talking about force from the direction of gravity. Now, we know at every moment the direction of gravity is away from the center of the earth. But we can change the orientation of our head. We can change the orientation of our limbs, our posture, and our balance is affected. So monitoring it on a continuous basis is very important. The 3 dimensions are loops filled with fluid, and the pressure that's generated by gravity in these fluid, as we change its orientation, tilting it right or left, forward or back, will produce changes in pressure on these maculae, these detecting organs. So here's a cross-section through the ampulla of a semicircular duct, showing a kind of a repeat of the structure we've seen before. Here are supporting cells connected to the sensory nerves. Now, this is now the vestibular branch of the vestibular cochlear nerves that are splitting to provide the nerve connection to the sensory apparatus inside these maculae. So here we have hair cells separated by their supporting cells and extending their hair-like projections up into this cupula, a sort of the cupula is a sort of a gel-like material with fluid on either side. So that very small changes in the direction of gravity, pushing from this side will distort the cupula in this direction, pushing from the left will distort it in the opposite direction, and bending these hair-like cilia, the stereocilia and the kinocilium, will send messages and basically depolarize this cell, sending a nerve impulse down this axon of the vestibular branch. So it is the change in orientation. Notice how if we change it so that the force is down this direction, we bend it one way. We hold it upright, so at rest, we're basically getting a force directly down on the top, and the cells can kind of be at rest. Basically rotating the duct. I'm sorry, I'm sitting here and the pointer's in the right position, and I'm trying to show you the change in orientation by rotating the mouse, which of course you can't see. But you can see tilted in the opposite direction, and the relative endolymph movement is pushing the cupula in the opposite direction. So the location in these macula, you can see the individual sensory cells and their hair cells, and this gelatinous material that they're encased in. But on top of it, there's a kind of an interesting formation. These crystalline purple structures on the top are called otoliths. Oto as in ear or hearing, and lith as in stone. So these are basically hearing rocks. And the structure of the individual maculae, you construct these sensory regions and then pile these otoliths on top. And they add to the distortion of the hair cells when you tip your head. Head in the normal position. Notice how gravity is pushing straight down, compressing the gel-like material, but not really distorting the position of these hair-like cells. But tilt your head back posteriorly, and gravity causes these otoliths to produce a force. It's a vector force to the posterior and inferior direction that pulls the gel, you notice. And it's the additional mass of the otoliths on top that will increase that distortion and bend the hair cells. That produces an output in the form of a nerve impulse for that region of the maculae. So those 5 receptors, the maculae, are located in positions where that kind of three-dimensional setup by the 3 loops, loop, loop, and loop of the semicircular canals will produce a complex 5-signal system transmitting information about what gravity is doing to their hair cells. Once that is done, it's collected here. In this case, the vestibular ganglion is shown, the 1, 2, 3, 4, 5 connections at the base of the semicircular canals. Here's the cut cochlear branch, which is carrying auditory information. But basically, the gravity information is coming near to the vestibular nucleus and up, eventually to the superior colliculus and relay center, and out to the cerebral cortex for processing about balance, or equilibrium, and the integration with, imagine what information would be useful to combine with the direction of gravity. Well, the most useful information would be the position of our body and the position of our limbs, those proprioreceptors from all over the body that are involved intimately with our muscles and our joints are constantly feeding in information. Compare that to gravity, and you've got a solution. You've got the problem of how do I keep from falling down? And the brain is constantly processing that solution. So in order to kind of wrap this up, I want to return to this section of the eye. You should be able, as a result of this lecture, to identify the different layers. We see the 3 layers, sclera, choroid, and retina. Notice that the retina, of course, is only here on the back portion. Here we have the lens and the ciliary suspensory ligaments, the ciliary body connected to those ciliary muscles that can distort the lens to change the focal distance of light waves. Here we have the anterior and posterior cavities. This opening would be the pupil, and these would be the structure of the surrounding iris. Out here enclosing and containing the vitreous humor would be the cornea of the eye. The retinal cells detect the light intensity and the light wavelength, depending on the kind of receptor cell you're talking about, and send nerve impulses from the actual 3D image here on the retina through these individual transmission fibers back to the occipital cortex. Now, in the optic chiasma, we're going to split and rejoin those. So the right side field is going to end up on the left side occipital lobe, and vice versa, left side field, the right side occipital lobe. But it's going to give us a real image, a virtual image on that wrinkled, extensive surface area, the visual cortex, of the occipital lobe. Now, kind of a little anti-intuitive, if I take something like a projector and try to project on a flat screen, the image comes out just fine. But if I took something as wrinkled and convoluted and folded as the brain surface and tried to project it, those curves would distort the image. But that doesn't matter because of the processing that's going on as we change sensation, the delivery of the nerve impulses, to perception, the actual image that we perceive. Now, that's tuned by our actual behavior. The first time we see something and we can reach out for it, we quickly learn how far away it is, what physical motion is needed to reach out and grab that. We have some depth perception. We have our visual acuity to guide our hand there, and we get better and better at that kind of targeting, and it affects the actual perception of the image that we see. So we see a very accurate real-world image as a result of our visual apparatus. Here is the master cross-section of the hearing and balance of the inner ear. So we have this external kind of focusing auricle with its fat and cartilage support forming this channel in the external auditory meatus of the temporal bone, leading to the tympanic membrane. The tympanic membrane vibrating and transmitting through the auditory ossicles to the oval window, setting up the vibrations in the cochlea that will be detected as sound. Here we have the semicircular canals and their included maculae, and the maculae will respond to changes in orientation of the head, tilting, bending, or inverting, in order to translate the pressure differences created in the endolymph into nerve transmissions here through the vestibular branch of the vestibulocochlear nerve, and eventually back to our equilibrium apparatus. So happily, we have completed chapter 28 and are ending chapter 17 on the special senses.